This is a guided reading for Chapter 7 for AP Physics. Also, this is being recorded with your built-in mic on your MP3 players you currently have. So if the audio quality is not good enough, please just let me know. So go ahead and open up your books to page 182. And this first section is on the impulse momentum theorem. And about halfway down the page, you'll see J equals F delta T. So when you see J in this book, that's the fat part of the fat app equation. Okay. Also, depending on how much you remember, there's going to be a lot you're going to be able to glance or skip over in this section. There's a few things that are new. They'll also define on page 183, you don't need to read that as long as you remember F delta T. On page 183, they also define momentum. Just be aware it is a vector, so it has magnitude and direction, and the direction comes from the velocity, so P equals mv. About halfway down the page 183, you'll see acceleration equals Vf minus V naught over delta T. And they will derive fat app from there down to the next grayish box with equation 7.4. If you do not remember how to derive fat app, you should be able to do that. So just go through the derivation to make sure that you can see what they're to get fat app from F equals ma. They started with F equals ma, ended up with fat app. Okay. If you remember that, you're all set. Go ahead then and turn to page 184. On 184, you'll see two example problems, example problem 1, example problem 2. You may want to look over and make sure that you know how to do those. Those are pretty straightforward problems. You don't have to read their reasoning as long as you understand their solution. So I would simply look at example problem 1, that first paragraph, and then look at the solution and make sure that you remember how to do that. Same thing for example problem 2. Look at the problem and then see if you can follow along with their solution that makes sense. If it doesn't, then read the reasoning. Okay. I would like you to read conceptual example 3, the hailstones versus raindrops. All right, welcome back. Hopefully that made sense to you. It is important that you have the reasoning that they had in there, so hopefully you also pay attention to their reasoning. That's a really good review of directions and m delta v. Okay. Check your understanding 1. Should be something that you can do as well. If you would like some more practice, you can do that. That's optional. If you want to make sure you've got what's going on in these first couple pages, that'll check to make sure conceptually you're okay. Now turn to page 186 and section 7.2, the principle of conservation of linear momentum. This is what we did a lot in physics, and we did it in one dimension. We said the momentum before is equal to the momentum after. Okay. And there were conditions on that we did it most of the time right before and right after collision so that external forces would be 0. Okay? So if you take a look, the key thing here, you don't need to read all this, but take a look at the two types of forces that act on a system, internal forces and external forces. Internal means that it's forces acting on each other within the system. External means it's outside the system. Okay? Then they go to great lengths to prove that momentum is conserved if external forces are 0. Okay, so if you have an isolated closed system, you can apply conservation of momentum, meaning that there's no mass gain or lost, and that the external force acting on the system is 0. Now, in a collision, are there external forces like friction and air resistance? Sure. That's why we did in physics right before and immediately after a collision, so that friction, an external force, didn't have much time to work on the system. Okay, didn't have much time to do work on the system. All right. If what I just said didn't make sense, you might want to talk to me or read this section, either or. Okay. Take a look at example problem 5 on page 188. That would be a basic problem from physics. Review that if necessary. It's two train cars colliding. Same thing for example problem 6 on page 189. There are two ice skaters pushing off one another. That might also be something you want to review for conservation of momentum. When you're doing problems with conservation of momentum, if you draw the before and after picture, you can do the work right below it. Obviously, in here, you're going to want to use subscripts. It's not like physics where you just write mv plus mv. Use some descriptive subscripts. You guys can handle it. And you'll be okay. The only thing to remember is that momentum does have a direction because velocity has a direction. That's probably the only place you'll make a mistake on the straightforward linear momentum problems. Okay. All right. They have on page 190, go to page 190, they have some strategies there to do the problems. If you follow what we did in physics, you'll be okay for linear momentum. Okay. On the bottom of page 190, collisions in one dimension. You actually should read this because we talked about this briefly, but we went a little bit. We went over it a little bit less in depth. So read section 7.3, which goes all the way to page 193. So you're at the bottom. You should be at the bottom of page 190 now. Stop and then come back after you are through section 7.3. All right, welcome back. Hopefully you have a good understanding of elastic and inelastic collisions at this point. In the real world, there's no such thing as a perfectly elastic collision, but you can get close. Okay. Collisions in two dimensions, section 7.4. This is where things are going to get new. Okay. In physics, we did everything in one dimension. The train cars never hit at angles. Okay. Or if they did, it was only conceptual. We never did any numbers with it. It's like everything else that we've done. You are going to be instead of doing something forces in the x and the y, you're going to be figuring out momentum in the x and the y. Okay. And then applying conservation momentum to the x direction, conservation momentum to the y direction. Okay, so you do need to read 7.4 in its entirety. It's a very short section, so go ahead and read that, and make sure you pay attention to the pictures. Welcome back. If you didn't look at example problem 9 on page 194, you should. Okay, now that's a case where they're putting the components into right away. If you need to separate that out to understand, that's fine. So if you take a look at x component there on example problem 9 where it's in bold, there's a cosine 35 at the end of one of those. That's allowing for the component of the velocity that's in the x direction. Okay, so it's just like dealing with velocities before. You got to break things down to the x and the y before you start the problem. Okay, and then at that point it just becomes two conservation momentum problems. One thing to keep in mind: if you do find if you ever have to find a momentum in the x and find a momentum in the y, and they ask for total momentum, it's just like any other vector. You have to draw the x, you have to draw the y, go from tail to tip, do the Pythagorean theorem, get the angle. All that same stuff that applied to vectors that were velocity and force still apply to momentum, and they will come into play on problems. Okay. Section 7.5 is center of mass, and you may skip all of that unless you want to read it. Center of mass comes in handy sometimes on problems. It makes things a little bit easier. Most of you intuitively will be able to handle those problems without using center of mass. So if you want to read that, you can. It gives an equation to what most of you can do just by looking at the problem and thinking about it on the multiple choice. So go ahead and skip 7.5 unless you're really interested in it. Section 7.6 is just more practice problems. The ones that are two-dimensional are ones that, there is no two-dimensional problem, sorry. So you don't need to read 7.6 unless you need more practice mixing momentum and energy into problems. That being said, you already have access to a video problem from physics last semester where you apply conservation of momentum and conservation of energy to one problem, the ballistic pendulum. If you don't remember the ballistic pendulum problem, you should watch that video. That ties together a lot of the stuff from both Chapter 7 and Chapter 6, minus the two-dimensional momentum stuff. So I would, if you don't remember that inside and out, that was problem 20 in Chapter 11 last semester, you're going to want to watch that video to recap how to apply both things and when to apply conservation of momentum and when to apply conservation of energy. That's it for this guided reading, and we are done with Chapter 7. The problems that you were assigned today in class is everything for Chapter 7. So test is coming up soon. Thank you.